Alrighty, cool. So, phylogeny. First of all, let's take a look at that gorgeous tree. Look at that gorgeous tree, just being a gorgeous tree. This is Unit 7, topic 9. It's got its own thing. Fantastic. So, phylogeny. Phylogeny is essentially a classification of organisms and determining their evolutionary relationship. I'm sure back in ninth grade, you guys talked about something like King Philip came over from whatever, right? King Philip came over from green spaces, like whatever it is. Now we have two up top here. We have a life and domain. And systematics is the word that we use to talk about the classification of organisms, determining their evolutionary relationship. Taxonomy is naming and classifying of species, and phylogenetics is, it says a hypothesis of evolutionary history, but essentially what it is it's doing this whole process of taxonomically and systemically being able to classify life into these categories based on genetics. It uses phylogenetic trees to show evolution. You can see over here my guy Darwin with his phylogenetic tree, and even if he was unsure about it, that was the observations he made. So yes, you can see here taxonomy, life, domain, kingdom, phylus, class, order, genus, family, genus, species, and then phylogenetics is kind of putting it into that tree of life. Great. So first of all, pause here to take notes. All right. So we use phylogeny to determine evolutionary relationships, and we construct these using a number of different pieces of evidence. The first is fossil records, so taking a look at different fossils and comparing them. We talked a little bit about that when we looked at comparative morphology. DNA, of course, to see what relationships they have genetically. Different protein structures. So we can see a relationship between organisms producing the same type of proteins. And then, of course, homologous structures. That's like, I have a radius and ulna in my arm, and so does a bat. Pause here to take notes. Awesome. So here's a phylogenetic tree. This is what it looks like. They're diagrams that represent the evolutionary history of a group of organisms. They're similar to cladograms, except the phylogenetic tree shows the amount of change over time. So over here you can see there's that single origin. And from the single origin, the furthest away here is animals and fungi and plants. And this represents a line. You can see here, this is where the genus Archaea separated from eukarya, and then bacteria, separated from the beginning. So you can see here, in the beginning, we had prokaryotes and eukaryotes, right? Sometimes you see them like this over here. I don't like these ones as much because it's kind of hard to trace back, right? But you can see evolutionary relationships between two species. Yeah. Great. Pause here to take notes. All right, cladograms are a little bit different. They're not as pretty, in my opinion. Each line represents a lineage of a species, and each branching point we call a node. So nodes represent common ancestors. So right here, there was a common ancestor, right between tigers, snow leopards, and then these three down below. Right here, there was a node representing a common ancestor between a tiger and a snow leopard, etc., etc. So nodes and all branches are what we call clades, and they represent common ancestors. A species and a clade have shared derivative features. So, for example, tigers and snow leopards have shared features that are distinct and separate from the lion, the tiger, and the jaguar, but they are all of the family Panthera. That's where the band got their name. There you go. There's a node. There's a node. There's a node. There's a node. The root is the common ancestor of all species. Again, we have that right there with the Panthera. Pause here to take notes. Great. And here's a cladogram. So cladograms emerge that emerge from the same node. We call them sister taxa. Remember, biology is feminine, so we have the sister taxa, sister chromatids, daughter cells, all of that. So we call them sister taxa. The lineage that evolved from the root and remains unbranched is the basal taxon. So you can see here, there's your basal taxon. It is the longest lineage that is unbroken, that doesn't have these things coming off of it. The answer to basal taxon is most likely crab. Crabs have been destroyed and reappeared as a species and evolved independently every time it's been extinct, and they keep just evolving back to crabs. So it's safe to say that crabs are the ultimate form of nature. Anyway, pause here to take notes. So you got the root here. There's a branching point. Here's a branching point. You can see they had one lineage here, and then 1, 2, 3, 4 species grew out of it. Cool. Cladograms. It's the same thing that we just did, but in a different shape. Derived character shared by clad members, right? So there's a derived characteristic, similarities that are inherited from the most recent common ancestor of an entire group. So you can see here, there's an ancestral trait here, and an ancestral trait here, ancestral trait there, and an ancestral trait there. But then it goes on to change in some way to a derived trait. So this trait is similar to this one and this one, but it is a little bit different. Ancestral characteristics are similarities that arose prior to the common ancestor. So you have, for example, if we're looking at this species up here with our derived trait, anything that had developed prior to this common ancestor of these other two species up here is considered to be an ancestral trait. Great. Now, pause here to take notes. Nature doesn't care about your feelings. There's an in-group and an out-group. There's a popular kids and a not popular kids. Most people are in the out-group. Most cladograms and trees include an out-group, and it's a lineage that is least closely related to the rest of the organisms. You can see here, here's your out-group, which is just one, it's like the first species that branches off of the common ancestor, and then the in-group over here. Which is where these in-groups share more traits with each other than they do with their ancestors. Great. So the groups could be different. Monophyletic groups include the most recent common ancestor of a group and all of the descendants. So for example, here's your common ancestor. There's a node up here in which it splits. So this is the most recent common ancestor and everything else that evolved from it. You have the paraphyletic group, which includes the most recent common ancestor group, but not all of its descendants. So you have a most recent down here, but see, this guy's kind of left out in the cold, not all of its descendants. And you have the polyphyletic group. This does not include the most recent ancestor. See, that's kind of left out in the cold, but all the other members of the group are included. Don't worry too much about the different types. Just know that they're grouped in different ways. Pause here to take notes. Oh, sorry, arrows. I forgot arrows. There you go. Pause here to take notes. All right, parsimony. So if there's conflicts among characters, use the parsimony principle, the principle of parsimony. It's a hypothesis that requires the fewest assumptions, right? It's kind of like the Occam's razor of evolutionary biology, right? Always assume or have the fewest assumptions, right? So you can say the most basic assumption that you can make is that the DNA changed. It's the most common reason for a mutation. Yeah. Don't start being like, oh, this bird must have gone over here because he was mad at his friends and he evolved differently and that's why they have different characters. No, most likely it's your DNA changed. Pause here to take notes. All right, let's practice. What is the common ancestors for butterflies, moths, and flies? Is it A? Is it B? Or is it C? Well, we got butterflies there, we got moths there, we got flies there. If you said C, you would be correct. What is the basal taxon? Oh, what is a basal taxon? It's the longest unbroken chain. It's hard to see when you do the cladograms like this, but if you did it like this way, it might be easier to figure out that it is beetles, right? If we were doing this over here, beetles, this one would be here. It would be the longest unbroken. This would be our wasps, bees, and ants. And from there, we would have butterflies and moths. And then finally, flies. Very cool. What's an example of a sister taxa? If you said butterflies, moths, and flies, you'd be right. It's because they all share this same common ancestor, this node there. Okay? Technically, no, just kidding. Just kidding. Sister taxa here because they share one common ancestor. There's one node there. Examine the data below. Plus represents the presence of a trait, minus represents the absence of a trait. Create a cladogram that would best represent this data. Did they give us an answer? They did. Okay. So the easiest way to do this is to know that this has the most negatives and this has the most positives. Okay, so the most traits are going to be up here, super evolved. So taking a look, we can see that that guy's C. Okay. Next, there are some traits that they have in common. A, B, C, and E all have the same traits in common. A, B, and C have the same traits in common. A and C, so on and so forth. So we're looking down here. We got 1, we got 2, we got 3. A is going to be next. Then we have 1, 2 for B, B, 1 for E, E, and finally D's down below here with no traits. Boom. Just like we drew. So C is your basal taxa, goes the longest without unbroken. A is next. They have the most traits in common with C. Then B, second most traits. Then E, third most traits, and D. Okay? So lowest down here is no, so least evolved. This is most evolved, if you want to think of it like that. Because it's really just an accumulation of traits. It's not necessarily evolved or not. Cool, good stuff. All right, examine the table below. Plus represents the presence of a trait, minus represents the absence of a trait. Create a cladogram. Now, this one's interesting. Do they give us the answer? Yes, they do. Don't look. We're going to do the same thing, but you can see here, A has the same amount of traits, positive traits. It's the most, so we're going to put that up here. But you'll notice that C and D have the same number of traits. So that's when you're going to do C on one side, D on the other. Ideally, these would connect, right? It's not going to look like a crazy person. right? Because they have evolved from a common ancestor here. That's why they have the similar traits. Then we can do B and E. See that? So if there's an equal number of traits that we're looking at, you put them equal on the same line with the single node down there. Let's check our answer. Boom. However you do it, if you want to draw the straight line and then have it go off on a branch, or if you want to have them branch like this, that's fine. Just know that they're branching off of at the same line. And still, E is kind of left in the dust over here, being the least amount of traits that we're studying. B is the second amount, C, D, and then finally A. So that's how you set those up. Great. Examine the table below. Which cladogram best represents the data? Oh, cool. All right. Okay, so let's see. We have 1, 2, 3 traits. We have 1, 2, 3 traits. It looks like C and E are similar in the 5th trait. So what do you think? I do, right over there. Boom. If you chose A, you are correct. Now here's why. So C is going to be at the end of the longest line. It has the most amount of accumulated traits here, okay? Off of there, there's E. A and B have these 2 traits. So B evolved and then A evolved past that, right? Because A has this 3rd trait. So A evolved with these 2 traits, A and B did, and then A broke from the pack and did that, which is why the B's up on the straight line and A is on the branching line. Finally, D is all the way at the bottom. Okay, just because the line is longer doesn't mean that it doesn't have the least amount of traits. So how you would draw this is you would recognize that C here has the most amount of traits, right? Or I should say the most amount of similar traits, right? Because we're kind of looking at similarities, which is why E comes next. It's not necessarily the number either, it's the similarities between the two. Okay? Then A and B are the same in these traits. D's last. Cool. That's it. I'll see you tomorrow. Uh-oh.